this, in the big scheme of things, is a strange lesson. Because, and I'm just being honest with you, I don't think in the past 5 to 8 diploma exams there's ever been a question that connects directly to this topic. But there is this objective in the program of studies in the course that says students need to know how to do a certain thing. And the value in going over this is that this thing that we're going to learn, which you actually should already know, is something that can be applied here, or to trigonometry, or to logarithms, or to exponents. And it has to do with solving equations graphically. The fact that today we're solving radical equations graphically is maybe secondary to the idea that we're solving equations graphically. Okay? But the types of equations we will be looking at will be radical. So we're going to review how to solve radical equations, because in Math 20-1 you learned how to solve radical equations algebraically. When you solve radical equations, it turns out that there's always a potential for an extraneous root. And I don't know if you remember what an extraneous root is. A root is a solution to an equation. An extraneous root is a solution you get to an equation when you do things algebraically and you've done them perfect. You have not made a mistake. You've done it the way it should be done. You followed the rules of algebra. But you know what? An answer you get is not a valid answer. And we need to remember that when you solve radical equations algebraically, you have to check every answer you get to see if it's correct. Then what we're going to be doing is looking at solving radical equations graphically. And that's what the last 3 bullets is about. We'll get into the nuts and bolts of that at the time. So number 1 gives you a radical equation, and we are asked for a statement of the restriction on the variable. Now listen very carefully. What we get for the restriction on the variable has little to no bearing on solving the equation. Okay? You're actually probably taught something in Math 20-1 that's incorrect about the connection between a restriction and a solution. Okay? And we're going to have to delve deep into that. But what is the restriction? Well, the restriction on any radical is that the radicand must be greater than or equal to 0. There is a little minor exception to that we will encounter, and when we encounter it, I will point it out to you. But the bottom line here is I'm telling you, you cannot take the square root of a negative. It's not possible. And the radicand in our equation that we are asked about, radicand being the word for what's underneath the radical symbol, the radicand is x plus 10. And that means that x plus 10 is not allowed to be negative, and we don't write what it's not allowed to be, we write what it is allowed to be. It must be greater than or equal to 0. X plus 10 cannot be negative. Well, we don't walk around talking about x plus 10. What we would like to do is make a decision about x. So all we do is we solve this little inequality, and we say that in this equation, if you want to put in numbers for x, you must put in a number for x that's bigger than or equal to negative 10. And what this looks like, I hope that nobody really needs to do this, but I find number lines to be really, really useful in terms of statements that are inequalities like this one. What we are saying is that if this is a number line showing values of x, x is allowed to be negative 10 or any number bigger than it. Okay? So that's what x is greater than or equal to negative 10 means, and that's a grade 8, 9, 7 kind of thing. Any questions with A? All right, solve this equation algebraically. So this is something that you learned how to do last year. In order to solve this algebraically, I take a different approach in high school math than maybe the textbook would. Your textbook would give you a set of rules for if there's a radical, a set of rules for if there's a fraction, a set of rules for if there's exponents. But I would say to you, you want to simplify things. You always want to work to an equation that's easier to work with. And if there is no radical, it's easier to work with, right? If we can get rid of the radical, then we have simplified it. Well, how do you get rid of a radical? You can square a radical to get rid of a radical. But since it's an equation, luck is on our side, we can square both sides of the equation. But in order for this to work, you have to, we say, isolate the radical first. So we take root x plus 10 minus 4 equals 0, and we say, let's set it equal to 4. By adding 4 to both sides, we can write root x plus 10 equals 4. Now I can square both sides. And quite frankly, solving this equation is child's play at this point. So I square both sides and I get x plus 10. Because the square root squared, these are inverse operations, they undo each other, equals 16. And then I can subtract 10 from both sides and end up with x is equal to 6. What we always want to do for radical equations is check, and the details in how we're checking this are very important. We do not put equals here in our check. We write down what the left side is equal to, which is root x plus 10 minus 4. We write down what the right side is equal to, which is 0. You cannot check to see if something is valid by assuming they're equal to begin with. And that becomes important in trigonometric proofs. And now we're going to check. We said x was equal to 6, so we put 6 in. Right, we're just substituting our value of x in there. And we simplify this. 6 plus 10 is 16. Root 16 is 4. And that gives us 0. And now we say that the left side is equal to the right side, so our solution is valid. And again, very simple example to warm up. Any questions with solving that equation algebraically or the checking? Now, taking you back to Math 20, in at least one place in the textbook, they say something that's wrong about these equations. And this is what they say. This was our domain of values that were allowable, right? What did we get for x? 6, correct? Is 6 in this domain? Is 6 in this part? Yes. Your textbook says because it's in there, it is a valid solution, and that's false. You're going to get answers that will be in that domain that do not work, which is why this is kind of a waste of time. It's something you need to know how to do for later, but it's got nothing to do with your solutions. Okay? All right. Find the x-intercepts of the graph of this function. So we're graphing y is equal to the square root of x plus 10 minus 4, and we're asked to determine x-intercepts of that function. So take a minute, go to y1 while I move my calculator onto this screen. Enter in the square root of x plus 10, then close your brackets on the argument for the square root, and then subtract 4. And I guess we can go zoom standard so that we're all looking at the same thing. So this is what it looks like. I can see an x-intercept there. There's a lot of, and I'm going to be using this idea with you from time to time, there's a lot of space here visually on our settings that is wasted space. We really don't care about any of this, do we? There's no information there, and we really don't care about this. So since zoom standard goes from -10 to 10, why don't we go from -5 to 2? And what that's going to do is give us a better, more rich picture of what's going on. This is a manual changing of the window settings. You go window, we're going to go from -5 for x to 2 for y. See, this is just bringing out more detail. I can see the x-intercept better. Now I'll remind you how to find an x-intercept. You go to your calculate menu, you choose 0. You choose 0. Remember that. It's not just remember it because you need to know where to go. Remember it because the word 0 is important. And then you have to put your cursor to the left of the x-intercept, which is the 0 of the function. Hit enter, put it to the right, hit enter a third time, and you get an x-intercept of 6. Okay. It's probably not a mind-blowing revelation to you that the x-intercept we get is equal to the solution to the equation. So the x-intercept is equal to 6. Whereas when we have 0 equals root x plus 10 minus 4, the root is x equals 6. Why is the solution to the equation the same as the x-intercept of the function? Because the equation is set equal to 0. If I said to you, find an x-intercept algebraically, x-intercepts are where y equals 0. So you would change this y to a 0, and you're really solving the equation that we solved in part B. Why I said at the beginning here as an introduction point that this is a valuable thing that you can use anywhere is I could give you the following equation. I could give you this equation, and you could have absolutely no understanding of what log base 2 of 6 is, but if you knew how to enter this for y, you could find the x-intercept. It doesn't matter what the equation is. I'm telling you, if you're stuck on an exam in math, any exam that has an equation, you can solve it graphically. So just to summarize this to make sure you get my drift, we call this a function. We call this an equation. Right? F of x can be anything. F of x can be 3x plus 10. So y equals 3x plus 10 is a function. 0 equals 3x plus 10 is an equation. The lesson to be learned out of this is the x-intercepts here and the solutions here are the same. And I'm blown away when we get into the first unit of trig and we solve trigonometric equations and people write the exam. Some of those questions are tough and some just don't even guess. You have a graphing calculator. You can enter it into your calculator and see the x-intercepts. Now, I prefer to do it a slightly different way, and I'll show you that in a second. Any questions with that whole first ABC? I don't know if it was an example or a warm-up. Any questions with any of that? All right, and as much as I say this is a weird lesson because you're probably not asked specific questions to it on a diploma exam, we're building our math muscles here through this lesson. There's value in working through this. What is the restriction on x in this equation? Well, x plus 5 must be greater than or equal to 0, otherwise you're left with the task of taking the square root of a negative, and that's not allowed. You can't do it. Which means x is greater than or equal to -5. Numerically speaking, what that means is if you locate -5 on a number line for x, you're saying x is allowed to be this number or greater than it. Don't get me wrong, I'm not saying every number in there will make the equation true, which is why this is kind of a waste of time. It doesn't really help you. It's just saying if you wanted to put a value of x in and evaluate something, you'd have to put in a value of x greater than or equal to -5. solve this equation algebraically and check for extraneous roots. So it's already queued up or teed up for us to square both sides. Right? It's a square root that's isolated, so we can square both sides. When I square the left-hand side, I get x plus 5. When I square the right-hand side, I get x squared plus 3x plus 3x plus 9, because x plus 3 quantity squared is x plus 3, x plus 3. I mean, I firmly believe that at any level in high school past grade 10 or 11, you shouldn't need to write it out that way, but even in my calculus class I do. Just to remind you, that's what we have to do. I would say, I think many of you would have just written x squared plus 6x plus 9. Maybe, maybe not. So we have to solve this. We notice that it's quadratic, so in grade 11 math you learn that you need to zero the equation to get x squared plus 5x plus 4 is equal to 0. We're setting it equal to 0 because that's what we do with quadratic equations. It has nothing to do with this lesson. And I look at this and I go, well, I'm not going to use the quadratic formula to solve this. I'm going to factor it because it's a pretty trivial task to see it's x plus 4, x plus 1. 4 times 1 is 4. 4 plus 1 is 5. Done. What do we conclude from that? Well, if the product of two things is equal to 0, then either of them can be equal to 0. If x plus 4 equals 0, then that equation will be true. And that means that x is equal to negative 4 and x is equal to negative 1. Bless you. Good? Okay. Before we check for extraneous roots, is negative 4 in this domain of allowable values of x? Yes. Negative 4 is, say, over here. It's in there. Is negative 1 in there? Now, these are both in there. And I'm telling you that your textbook, I don't know how this mistake got through. Your textbook would conclude that since they're both in there, they're both valid solutions. And that's wrong. It's an incorrect conclusion. Whether that's a true statement or not, and it isn't, is irrelevant. That's not how you check. We need to take the original equation, which is x plus 5 as a radical, is supposedly equal to x plus 3. And we need to do this twice. We need to do it with negative 4 and we need to do it with negative 1. And you need to show your work here. This isn't a matter, no matter how simple it is, of you just looking at it and going, yeah, it works, or yeah, it doesn't work. So we end up with so left side, right side. We end up putting in negative 4 here, and we end up putting, well, let's do this one first. So negative 4 plus 5 is 1, so we're left with root 1. And then over here, I forgot to put my negative 4 in. Negative 4 plus 3 is negative 1. Root 1 is 1, but this is negative 1. Negative 4 doesn't work. We have not done anything wrong. I mean, some of you might kind of tiptoe around in your head why this happens. Basically, it happens, and I don't want to get into too much detail, but your original equation has a square root. And when you square both sides, you end up with a quadratic. And when you solve a quadratic, at some point you take the square root, maybe in the quadratic formula, which has a plus or minus. But the plus or minus wasn't there to begin with. And that's the nature of why you get an extraneous root here. So this is not a solution. It's what we call extraneous. And what that means is you would go back up here and you would be very clear. You would say no or not a solution. Do not just put an x beside it because somebody might think you're saying it's x. Don't put an x for wrong, cross it out. Now we try the other one where we're putting in, what are we putting in? The other solution was, oh, I crossed out the wrong one, didn't I? My apologies. Not sure what I did there. Well, I know what I did. I'm not sure why I did it, but anyway. The negative 4 is not a solution. We still have yet to try the negative 1. So we put in negative 1. I mean, I think most of you can see this is going to work right out of the gate here. Negative 1 plus 5 is 4, so you get root 4 equals 2. You get 2 and 2. The left side is equal to the right side. So we can go up here, and I like to communicate this by doing that. Again, just because a supposed answer is in that domain of restricted values for x doesn't make it a solution. You have to check it. All right, let's solve this graphically, and I'm going to do it in two ways. In order to use the method that I talked about here, let me go back and show this to you. In order to use this method here, which is what your textbook talks about, you have to zero the equation. You have to have it equal to 0. Not because it's quadratic or anything like that. It's just because you're saying y equals 0 for x-intercepts. So we have to take that equation, the original equation, and I wanted to stress something else here. Sorry, I'm going to back up. When you check your solutions, you have to check them in the original equation. Don't put them in anywhere else, because they might work elsewhere. So I'm going to take this equation and zero it. I'm going to write 0 equals root x plus 5 minus x minus 3. Could I have written y equals x plus 3 minus root x plus 5? Sure. But I decided to subtract x and subtract 3. All I need to do is find the x-intercepts of this graph. What is scary is the wrong word. What is maybe scary sometimes with this method is you don't know what this graph looks like. You have no way of knowing what this graph looks like until end of May, where we might start talking about things like this. So don't be surprised if it looks a little wacky. Y is equal to the square root . Try that again. Y is equal to the square root of x plus 5. Make sure you close the brackets on that argument. Minus x minus 3. Let's go zoom 6 just as a starting point. Oh, I think that's pretty good. You can clearly see there's an x-intercept there. You can also see there's one x-intercept. And if we find the value of that x-intercept by going to 0, y 0, because it's where y is 0. And we put our cursor to the left and then to the right and hit enter. We get negative 1. That's the solution. And notice that we had that other extraneous root of negative 4, but you don't see it. Sometimes you are asked to find an extraneous root. You can't do it graphically. You have to do it on paper, and the extraneous root will be the number that doesn't work. So the solution is still negative 1. I like this better. I don't know why I prefer it. I would just say this. Why not do this? Why not just graph two functions and find out where they cross? And whatever the x value is where they cross, that's the x value that makes the equation true. Well, I know why I like it, and I'll explain it in a second. So I'm going to graph y equals root x plus 5 and y equals x plus 3. And I'm going to go zoom standard. The reason I like it is when I go through the process of finding the intersection point, I don't have to scroll around. As long as you can see the point of intersection, and as long as it's only two functions, then all you do is go to your calculate menu, choose intersect, and then hit enter 3 times. Now, you have to make sure that you're on a function to begin with. If, for example, my cursor landed someplace over here to begin with, it won't work. I might have to scroll over there. But then I just hit enter 3 times. -1. I don't care that it's 2. I don't care what each side is equal to. I care that they're equal to each other when x is -1. So the solution is -1. Any questions with that one? Right? What do you notice about the extraneous root found when you solve the equation algebraically compared to when you solve it graphically? Well, you can write this down. I'm not going to write it. You don't see it graphically. You will never know that there was an extraneous root when you do it graphically. So although graphically is a nice way to cheat the system and to weasel and maneuver your way to the answer without worrying about doing any real math, if you are asked for the extraneous root, you can't do it graphically. Got a couple more quick questions to do. Solve this equation algebraically. So we're going to take both sides of this equation where the radical is already isolated and square both sides. And get 3x squared minus 5 equals x squared plus 8x plus 16. Are we on the same page there with that? Okay. It's quadratic, so we need to zero the equation, of course, and get 2x squared minus 8x minus 21 equals 0. And I just want to double check all of that. All of you should double check it as well. 60 eyes are better than 2. 3x squared minus x squared is 2x squared. We have to subtract the 8x and subtract the 16. Looks good. Is this factorable? Well, maybe. I don't know. But I would do the b squared minus 4ac deal that we've talked about at least once, that if b squared minus 4ac is a perfect square, then it's factorable. So we're taking -8 squared minus 4 times 2 times 21, negative 21. I'm getting 252, but that's just in my head, so that may not be right. I can tell it's not 252. Let me do it again. How about 232? Okay. So this is 232. The nice thing is, since 232 is not factorable, the nice thing is we know what b squared minus 4ac is equal to, and if it's not factorable, well, then you have to use the quadratic formula. Whoops. Then you have to use the quadratic formula. Well, you don't have to. If you want to solve it by completing the square, be my guest. But I don't think anybody does. And b squared minus 4ac is a big part of the quadratic formula. So x here will be equal to negative b, which will be positive 8, plus or minus root 232, all over 2a, which is 4. And we have to be able to simplify root 232. I'm looking at 232. I see an even number. My first line of attack is to say, is it divisible by 4? And if it is, I'll go one further and I'll say, you know what? Is it divisible by 16? Because sometimes that happens. I don't think it is divisible by 16. When I divide it by 4, Paige, what do I get? 58? And I don't think there's any perfect square in 58 because 58 is 2 times 29. What that means is root 232 is the same as root 4 root, you said 58, which is 2 root 58. So we get x is equal to 8 plus or minus 2 root 58 all over 4. We can factor a 2 out of the numerator, and that 4, you certainly don't need to write 2 times 2 for the 4. I'm pointing out that 4 contains a factor of 2, and the numerator has a factor of 2. I'm not sure that I've mentioned this in this class. A factor can be identified as being something that is in brackets multiplied by everything else. And that is what allows us to cancel things. So the x-intercepts are 4 plus or minus root 58 all over 2. 4 plus root 58 all over 2, and 4 minus root 58 all over 2. And you could certainly calculate those. Why not? Got something better to do right now? Well, no, let's calculate these. What's 4 plus root 58? This is the way I do it, and then I always go equals. Divided by 2. There's one of our solutions. Well, I want to be careful. That's an approximation to one of our solutions, because that's an irrational number. We can't write it in decimal form exactly. It's about 5.81. And then my other one, whoops. My other one will be 4 minus root 58 all over 2. So about 5.81 and about negative 1.81-ish. I'm not going to bother writing anything for B. I think you're getting the gist. Let's solve this graphically. See, we didn't check for extraneous roots here, did we? It would be quite complicated. Not really. What you would do is this. I'll show it to you briefly. Do you agree this is one of my supposed solutions? It's an answer. I'm going to store it as A. Some of you like to scroll up and grab things. I like to store things. So STO is the store, alpha A. And now if I want to check out this equation, I can take the square root of 3 times my answer squared minus 5. This is the left side. And I can take my answer plus 4. This is the right side, and they're equal. But there's not really a nice way to do it on paper. So let's solve this graphically. Excuse me. The square root of 3x squared minus 5. I'm going to go equals x plus 4. I'm going to solve it using the y1 equals y2 method. I seem to recall that we can catch that intersection point in the top right corner, but you might want to regraph it with a higher value of y so that you can definitely see without a doubt where they intersect. We'll just do one. Calc, intersect. I'm going to put, where's my cursor? Where's my cursor? See, right now my cursor is where one of the functions doesn't exist. It's kind of in the middle. So I'm going to scroll. There we go. It's over here somewhere. Enter, enter, enter. There's that number for x. And if you do the same thing to the other side, you'll get the 5.81. Finally, one more example here. And As much as this lesson is about solving things graphically, I think solving equations graphically is sometimes more hassle than solving them algebraically, because you have to worry about window settings. Take a look at this question, and I have a typo up here. I know that it is not in yours. There's a 0 here as a subscript on that V, isn't there? In your handout. Okay. So this is a physics formula. It says the speed of a roller coaster that has an initial speed of v sub 0, if it falls from a distance d, is given by this formula, where a is the acceleration due to gravity. It says one particular car has an initial speed of 8 feet per second. Well, that's v0 then. And it reaches a speed at the bottom of 130 feet per second. That's v. And this is the acceleration. What is the height of the drop? What is d? All we're going to do is we're going to put those numbers into this equation. So we're going to have 130 equals the square root of 8 squared plus 2 times 130 times d. Nope. 2 times 32 times d. It's a radical equation. I think, honestly, you guys, this is so simple to solve. Why would you want to solve it graphically? Look what this equation is. It is 130 equals the square root. 8 squared is 64. 2 times 32 is 64. And we solve this equation. It's simple. Square both sides and rearrange for d. The idea that you're going to do this graphically, I think, is a little wacky. I don't think you want to do that. So when I square both sides, I get, and you'll have to check my mental math here, 16,900 equals 64 plus 64d. Good, thank you, Paige. I subtract 64 from both sides and get 16,836 equals 64d. I divide both sides by 64. And if I wanted to, I could probably get close in my head, but the limits of my mental powers kind of diminish right there. Paige, can you let me know what you get? So let's say 263 feet. I thought meters at first, and I thought, wow, that's a big drop. 263 feet. Football field is about 300 feet in length. So give you an idea of the distance. And that's it. That's the lesson. The big takeaway is you can solve most equations graphically. I say most because there's some wrinkles in that idea that we learned today. You can solve most equations graphically. This is a good review of how to solve things algebraically in case you're asked to find an extraneous root. Again, if you're asked to find an extraneous root, you need to solve it algebraically and then find out which of your answers doesn't work. And that will not be revealed on a graph. You won't see it on a graph. I might give you a multiple choice question that gives you an equation and says, what is the extraneous root A, B, C, D? And I will always have answers here that every single answer you put in, none of them work. So that you can't do it that way. You still are forced to do it algebraically to find out which answer you get is on the list that doesn't work. By the way, if I did have a number in here and you put it in and it worked, then it's obviously not the correct answer. 1 to 4 on the following page, and I also have a brief handout for you with 5 questions. Some of them quite challenging. They do not cover today's topics. They go all over the place. Transformations, square roots of functions, inverses, all that. So I'll hand that out to you, and that's what you're working on today.